Good morning, students. I would invite Himanshu sir to start the session.
Okay. Good morning, everyone. So in the last class, we have discussed about optical isomerism, dextrorotatory, levorotatory, chiral carbon, chiral center. Okay. And also about the projection formula in the optical isomerism. And we have discussed the wedge and dash form, Fisher form. And today we'll do a type of nomenclature that is called configuration. Nomenclature in optical isomerism. That is configurational nomenclature in optical isomer. So this is the topic, and here we will go for the first DLN form. First type we'll go for DLN L system. Okay. So the compounds which rotate the plane polarity in the right direction. Okay. So they are known as, they are having a positive rotation. That's why we are saying it as dextrorotatory. If the compound is showing left, or you can say anti-clockwise rotation of the plane polarized light, then they are known as what? Levorotatory. Okay. So this particular method is used to relate the configuration of sugar. Relate the configuration of sugar and amino acid. Sugar and amino acids. So sugars, we are talking about the saccharides, so you can say we are talking about the carbohydrates. Okay. So for example, I'm taking one example. HC, or in the Fisher form, if I'll make CHO, CH2OH, OH, and we have H. Okay. So this is known as glyceraldehyde. Glyceraldehyde, and this is glyceraldehyde show the positive rotation. So I'm writing D in front, and just because of the positive rotation, I'm writing plus here. This is called D plus glyceraldehyde. It means this particular compound will show the positive rotation of the which light? Dextro levo. Oh, which light? Plane polarized light, you say. Okay. If I'll make a mirror image of this particular compound, what will be the compound? Here we have CHO, then at the bottom we have CH2OH. On the left hand side it will be OH, on the right hand side it will be H. So if the compound is dextrorotatory and we are making a mirror image, the another compound is also the dextrorotatory, but just there is a change in the configuration of different type, and we will learn it as what? R and S. But here the rotation will be levo minus glyceraldehyde. Okay. The main thing what we're gonna do is here is R and S form. Same example we can go for the mirror image in the, or basically instead of this plane or rotation of the plane polar light, you can say if the OH is present on the right hand side, write D. If the OH is present on the left hand side, write L. You can use this type of configuration also. Okay. So the main thing what you have to remember is R and S configuration. Okay. R and S configuration. Okay, certain rules are there. Rule number 1, but we have to see that the first we have to go for the priorities. So priority of the groups which are attached with the asymmetric carbon, you can say priorities are given to the groups which are attached to chiral carbon. Okay, what was chiral carbon? What was chiral carbon? Anyone? No one knows what is chiral carbon. Those who were in last class, yesterday's class. Chiral carbon, stereogenic center or stereo center, or you can say asymmetric carbon. No one remember? Chiral carbon is that carbon which have all valencies occupied by the different atoms. All valencies which are occupied by the different atom. For example, carbon having all the valencies occupied by, for example, I can say we have here uh, we have here Cl, we have here Br, we have here I, we have here CH3. So all the valencies are occupied by different atom. That's why we'll say this particular carbon as chiral carbon. Okay, so priorities are given to the groups which are present, which are attached with the chiral carbon. This is the second rule. First rule, sorry. This is the second rule. If I'll say the lowest priority is given to the group that is brought to the bottom of the Fisher projection by two or even simultaneous exchange. You have what you have to do. You have to you can say the one having the lowest priority. Lowest priorities are brought to the bottom by simple exchange. Third point, I'll show you how we'll do. Then you have to draw from the first priority group to the second priority group to the third priority. You have to go like first to the second, then to third, and then to fourth. You have to draw arrow. You have to draw arrow. If condition is, we have two conditions in this particular, two condition. First condition, if clockwise, then the projection is R. Then the projection is R. If anti-clockwise, then the projection is S. Okay. If there is a rotation clockwise, then we say it as R. If the projection is left hand side, or you can say anti-clockwise, you'll say it as S. Got it? I'll show you some examples. See, we have to give the priority. What we have, first example, we are taking as CH2OH, Cl, Br, CH3. So if I'll give the priority, here Br having the first just because higher atomic mass. Okay. Then second, if I'll say chlorine have the less mass. Then third, if I'll give, it will be CH2OH. And fourth priority is given to the CH3. You can calculate the mass. Okay. Our priority is how we have to give the priority as I told you in the last class. Okay. So you have to go from 1 to 3, not 1, 3, 2 or any other order. You have to go like from first to 3 and then we will go for the fourth. So if you will see from the first, I'm making the arrow and the arrow is going anti-clockwise. And if anti-clockwise rotation, the projection is known as And the projection is known as, am I audible or not? Anti-clockwise, S. Clockwise, R. Yes. Understanding my point or not?
Yes, sir. Yes, sir.
So this is S or this is R? See, we are going 1, 2, 3. Anti-clockwise arrow is anti-clockwise. So this is S
S.
configuration. Okay. One more example I'm giving. I'll give you example. You have to tell me what is R, what is S. Okay. COH, CH3, here Cl, here NH2. Okay. Okay. Completed. Yes. Tell me.
S.
YS.
Anti-clockwise.
So you have first priority is given to
Oh,
hmm?
H2N. I think so.
H2 in first priority. Okay. Second priority.
Cl.
Okay. First calculate the mass. NH2. Or you are telling like atomic number of the first atom. How you are giving the priority? Just because we have COH, COH3, so we have to go for the see second priority will be given to the COH just because if you calculate the mass, it will be more. Then third priority is given to
CH3.
yes, and fourth priority is given to Cl.
Cl.
Okay, so you have to exchange the position in such a way that the by just one shifting. Okay, if you are shifting one, then second one will also shift. So while shifting, I have to bring the fourth priority group downward. So I'll shift these two, and if I'm shifting these two will also shift. Okay, so it will be in NH2 at the above, COH at the left side, then CH3, and then we have here Cl. So now write the priority first, then it was second, then CH3 was third, and it was fourth. The first, second, third, they will go anti-clockwise. The rotation will be S, it will be S. Okay, one more example I'm giving. Example is H, CH2, CH3, CHO, then N2H. I'm talking about NH2 over here, okay? So tell me fast.
Sir, it is also
No,
anti.
sir, it's R.
Okay, let's give the priority first, okay? First priority is given to NH2.
Yes, sir.
Second priority is given to CHO.
CHO.
Third priority is given to CH2, CH3. Fourth priority is given to hydrogen. So you have to exchange the position just so that the hydrogen will come at the down. So if you'll do the changement, how you'll do the change? How you'll change? How you will change the position? Like this. Okay, so CH2, CH3 will come at the top, hydrogen will come at the bottom, and these two will exchange the position. 1, 2 will exchange the position, so it will be CHO left hand side and NH2 right hand side. Now priority, first priority, second priority, third priority, and fourth priority. So we have to go like 1, 2, 3. So if I'll go from the 1, 2, 3, the arrow will rotate to the anti-clockwise and anti-clockwise rotation. No, sorry, clockwise rotation. This is a clockwise. So it will be R. Okay, last example. CHO, OH, H, CH2OH. Yes, do it fast.
R only, sir.
Okay, tell me the priority. First priority is given to,
OH, sir.
second priority is given to CHO, third priority is CH2OH, and fourth priority hydrogen.
H, yes, sir.
Okay, so you have to exchange these two position and these two position. The compound formed will be above, it will be OH, left hand side, right hand side CHO, left hand side here CH2OH, hydrogen will come at the bottom. Okay, so the rotation will be like this. So again, it will be R. Very good. Got my point?
Yes, sir.
Okay. Next thing is, just give me 1 minute, okay? Okay. Next one is the calculation of the number of optical isomers. Calculation of number of optical isomers. So we have 3 conditions here. First condition, when molecule is unsymmetrical. It means first what you have to do in this particular case, first what you will do, number of optically active isomer. You have to calculate number of optically active isomer. How you will calculate? That will be A equals to 2 ki power n. What is n here? N is equals to number of chiral carbon. Okay. So second thing what you will do, okay, I'll tell this another 2 example in next page. Second thing what you have to do, number of mesoform. Okay, number of mesoform in the asymmetric, unsymmetric means mesoform can be calculated by just giving a plane. Okay, so then unsymmetrical carbon, then mesoform will be calculated as 0. The number of racemic mixture, it will be R is equals to A upon 2. R is racemic mixture, A is, you can calculate from here, optically active isomer. Okay, and last thing what you can do in this is total number of optically active isomer, you will use the formula A plus M is equals to 2 ki power n. Okay, either just add the A or M. Okay, or you can use directly the 2 ki power n. Second thing is when the molecule is symmetrical. when molecule is symmetrical. And in this condition, the molecule has even number of asymmetric carbon. It means even number of chiral carbon. It means more than one chiral carbon can be present. So first thing is say number of optically active isomer. You have to calculate. It will be A is equals to 2 ki power n minus 1. It was 2 n ki A ki power 2 ki A is equals to 2 ki power n. Just when the compound was asymmetrical, and how here we are using as A is equals to 2 ki power n minus 1. Number of mesoform. For calculating the number of mesoform, you will use m is equals to 2 ki power n upon 2 minus 1. Third thing, number of racemic, same formula. Number of racemic mixture, R is equals to A upon 2. Total number is A plus M. You have to calculate A, you have to calculate M. Add them, total number of optically active isomer will be calculated. Third case will be when the compound is symmetrical. It means a chiral carbon is present, but in this condition the chiral carbon is in even number. But now third condition is symmetrical with odd number of asymmetric carbon or chiral carbon. Number of optical isomers, same. Optically active isomer will be equals to A is equals to, here the formula is 2n minus 1 minus 2 n upon 2 minus 1 upon 2. This is the formula. Number of racemic mixture is equals to A upon 2. Total same, A plus M. M we will calculate same mesoform. So although there are less chances of getting question from this topic in your academic as well as in your exam. Okay, I just gave you the formula. I'll teach you how to calculate. We'll do some examples. But before that, we have to complete lots of things, which is more important. So first we'll do conformation isomers. Conformational isomerism. And conformational isomerism, what will start with the, see, why this conformational isomer occur and what is conformational isomer? Conformational isomer generally arises due to the symmetry. Arises due to symmetry. Due to symmetry in the molecule, or you can say due to the rotation. The rotation about, okay, in which there is a restricted rotation. Unsaturated carbons or saturated. Restricted rotation. Double bond or single bond. Restricted means when we cannot rotate the bond. Restricted rotation is always present in the double or triple bond. So the conformational isomers generally arises due to the symmetry of the molecule, rotation about the carbon-carbon single bond. Carbon-carbon single bond, which is free. Just because around the single bond, it is free. You can have an example. You can put your pen on the hand and just imagine the cap of the pen is one compound, one molecule or one atom, and the end of the pen is another atom. So you can rotate the pen easily. Okay. So if it is a free rotation around the axis, so that's why we are saying we are saying it as it can form conformational isomer or rotational isomer or rotamers. Okay, so first thing we have to do that there must be a rotation on the single bond. Second thing, there must be a symmetry. Third thing, what you have to remember that conformational isomers are also known as rotational isomer. Why we are saying rotational isomer? Just because there is a rotational isomer, or you can say rotamers. Getting my point or not? What are rotamers? What is rotational? What I'm saying? Conformational. Getting my point or not?
Yes, sir.
Okay. So first type we are saying we are taking example of ethane. We are taking the example of ethane, and in the ethane molecule, first conformation we will make is of sawhorse projection. Sawhorse projection. See how sawhorse projection. First of all, the basic structure of ethane is make the basic structure. It will be C, H, 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 and here H. This is C2H6. This is the basic structure. If I'll make a sawhorse projection, so you don't have to show the mid carbon, and the compound will be like, just make a tilted line. This is the back carbon, this first point and second point. This is the back carbon. We have one hydrogen here, one hydrogen here. Hydrogen, hydrogen, hydrogen. Of the second carbon, hydrogen, hydrogen, and hydrogen. So this is, you can imagine this particular thing in the 3D. That this particular, first this hydrogen is behind this, above this particular hydrogen. This hydrogen will on the front of this carbon, hydrogen, and this will on this hydrogen. So this, when all the front hydrogen is covering up the back hydrogen, that type of isomer, this type of projection is called sawhorse projection, and this is called eclipsed form. Eclipsed form. So what you have to do, just because I told you that conformational isomers are having a free rotation, so just you can imagine like holding up the first molecule and rotate the bond. So if I rotate the bond, so the first carbon will be as it is, and the second there will be a rotation. So second will rotate like this. Now none of the carbon is covering up the back carbon. So this form is known as staggered. So what I have done, I have rotated this particular bond in this way. So when I rotate this particular bond, it formed a staggered form. So two type of sawhorse projection is there. One is eclipsed form, another one is the staggered form. Got my point? Yes.
Yes, sir.
See, you have, what is the main point? That first carbon you have to show on the lower left side. This is, see, if I'm making the line this is the lower side, this is the upper side. So that is the lower left side, first carbon on the lower left side, and second carbon on the upper right side. Okay, if I'll make, this was a sawhorse projection. Second type I am making as of ethane only, Newman projection. Newman projection. In the Newman projection, what you have to do, you are viewing the molecule along the bond joining to a carbon atom in such a way that the atom near to you is showing at the first. For example, the structure was, basic structure was CH3, CH3, H3, and H3. The first carbon, this is the first carbon, this is the second carbon, or you can do the vice versa in this case. So the first carbon will be shown by a point. The first carbon is shown by a point, and three hydrogen will be there. So this will be H, H, and H. This is the first carbon in this Newman projection. While the carbon which is away from your eyes, it means I'm talking about second carbon, which will be represented by a circle. Second carbon is represented by a circle, and it still have three hydrogens, so we will make it like dotted line. So in the 3D, if you want to imagine, it will be like the the frontal carbon is shown by the point, and the second carbon is just coinciding on the back, and all the back carbon is shown by the dotted line, while the above carbon is shown by the dark line. So this is called Newman projection, and Newman, just because it is covering, so we'll say it as eclipse form. Now just hold up the first carbon and rotate the back carbon. The bond formed will be, see, the front carbon will be as it is, so it will be H, H, and H. Second carbon is shown by the circle. Now it will be like, now they are not covering, so it is known as staggered form. Got it?
Yes, sir.
First carbon is shown by point,
Dot.
dot or point, yes. Our back carbon is shown by circle. Okay, so this much I think you know now. Okay, let's do another example. So now you have to make the Fisher projection and the Sawhorse projection. Okay, I'm giving you the structure. Second example, and you have to make the Fisher projection first. Oh no, not Fisher. Okay, just write the Fisher projection, write the Newman projection, write the Sawhorse projection. Okay, can you do? Yes or no?
We will try, sir.
Yes, good. Okay, just try. See if I'll make the Sawhorse projection first. Okay, so can I make it like this? I'm making, and you have to make this Sawhorse projection. Oh, I'll make this Sawhorse eclipsed. I'll make the Newman eclipsed. You'll make the Newman staggered, Sawhorse staggered. So just see. First tilted line, then three. Okay, on the first carbon, what we have, we will use CH3 here, BR here, and H here. Second side, what will you do? BR here, H here, and CH3 is here. Now, this is the Newman, Sawhorse eclipse form. According to this, just make the Newman projection as well as the staggered form of the Sawhorse.
Sir,
Yes.
in the horse form, you have written Br opposite to hydrogen also. Then how it will be eclipse?
Okay. Wait. Opposite. Okay, Br here and H here. Yeah. Now it's eclipse. Good. Now just make this staggered form. What you'll do, first carbon will remain as it is. You have to rotate the bond and then make this structure. If you'll make this eclipse form, the structure will be like, check your structure if you have made. Or see, you can rotate anyone, okay? This is a free rotation. Okay, as I told you, just remain the first carbon as it is and rotate the last one. So just make it like this. The CH3 will remain as it is, Br on the left side, H on the right side. And if I'll make the eclipse form, the Br will come at this position, H will this position, CH3 with this position, and hydrogen at the bottom. Yes. Is this correct?
Yes, sir.
So you have made this same structure.
Yeah, sir, but I've written at elements in different places.
It's okay. It can be in the different, but this in the staggered eclipse form, it must cover, and in the staggered form, it must not cover. That's it.
Yeah.
Just one rotation. Okay. Okay. According to this, if I will make the Sawhorse projection, first carbon, CH3, then Br, then H. Again here we have here CH3 dotted line, and we have Br. Here we have H. If I'll make this first dotted line dot, so it will be Br CH3 H CH3 Br and H. So I think you can make it like this now. Okay, it's not that much stuff. It's easy, and you can do it. Okay, let's discuss about the conformation of butane. Conformation of butane. What is the formula of butane? It's CH3, CH2, CH2, CH3. Okay, so I'll directly make the conformation Sawhorse projection of butane. Okay, so just first basic structure is CH3, C, H, H, C, H, H, and CH3. Wait a minute, okay? So if I'll make the just give me 2 minutes and do one thing. Just make the Sawhorse projection, eclipsed and staggered form of this particular compound. Fast. Okay. So basic, if I'll make eclipsed form first structure will be like this only. Here we have CH3, we have H and H, and at the back we have CH3, one H here, another H here. So this is called fully eclipsed form. Okay, fully eclipsed form. Just do a 60 rotation by 60 angle, 60 degree. So the compound form will be CH3, H, H. CH3 will come at this position. Here H will become this position. H will come this position. So you can say the angle between methyl and methyl in this particular case is 0. And this, in this condition, angle between the methyl and methyl is 60 degree. Okay, this form is called Gauche, Gauche, or you can say staggered form. Okay, so do one more rotation 60 degree. The compound obtained will be front carbon as it is, CH3, H, H, okay, and back carbon, you'll see again. Now if I'll rotate again 60 degree, the hydrogen will come here, this CH3 will come at the back of this, and this hydrogen will come at the back of this. So this will also considered as the staggered form. Okay, this is not fully eclipsed form, not fully eclipsed. It is known as eclipse only. And theta, angle between methyl and methyl here, 120 degree. One more time, if I'll do the rotation by 60 degree, so this will come this side, CH3 will come this side, BH will come this side. So the compound formed will be CH3, here CH3, here H, here H, H and H. So this is known as anti-form, or you can say also staggered in the basic language. Now the theta between the methyl and methyl is 180 degree. So you can see by just 60 degree rotation, we got the 4 isomer. So if I'll talk about the relative stabilities of 4 conformation of N-butane. First stability, highest stability of NT, then GAUCHE, Gauche form is also known as Q form, and then partially eclipsed, and then you'll go for the fully eclipsed. See why NT form is having the highest stability, just because they are present at the anti to each other. It means the repulsion between the atoms will be less, and if the repulsion is less, it means the compound will have the more stability. So you can make the 4 structure if you want to make. Done. You have to do just 60 degree rotation only. First one is eclipse, second one is Gauche, third Gauche is also known as Q form. Okay, or also you can say it's Q form. Okay, just do it. Done? Okay. So let's talk about the cycloalkanes. Cycloalkanes, and we will do the conformation. See, cyclopropane, cyclobutane, these are planar structures. Okay, we'll talk about directly about the cyclohexane. In the cycloalkane, we'll talk about the cyclohexane, and the basic structure what we have learned is this one. So if I'll say cyclic structure, okay, and here you can see all the carbon are singly bonded. So just tell me, single bond have which hybridization? Single bond have which hybridization? Huh? sp what आगे? sp2 sp3. Yes, Bhavna is there in the class or not? Not. Bond angle in cyclohexane. See, basically, if I'll say the bond angle of sp3 hybridized carbon, just because if the single bond is present, the hybridization is sp3, and the bond angle must be 109.5 degree, or you can say 109 degree point 28 minutes. Okay, either 109.28 minutes, or you can say 109.5 degree. So the bond angle must be this much. But in cyclohexane, just because due to the ring formation, the bond angle is not 109.28 minutes. The bond angle is less. So why? So just because there is a strain between the molecule, just because the bond angle is not this much, there is a strain, and due to which the cyclohexane don't exist in this particular form. So we'll make the conformation. If I'll make the conformation of cyclohexane, you have to remember them. The conformation of cyclohexane. First one is the chair form. This is called chair form. And chair form is the most stable form. Then let's move with the another example, that is half chair. So half chair is typical to make. Half chair is like this. This is called half chair. These are the conformations of this, you can say, cyclohexane. Okay. Third conformation is twist boat. Twist boat. It means the boat is twisted, sort of. This is known as twist boat. And then the last one is boat structure. This is called boat structure, or this is the less stable, you can say, least stable form of cyclohexane. Okay, so just because of the torsional strain between the atoms of cyclohexane, it exists in the different conformations, and the fourth conformation is chair form, which is the most stable form. Then this half chair, then you can say the twisted boat, then you can say the boat. See, if we'll make the graph will be in this order. See, if this is the potential energy and this is the relative energy of cyclohexane, you'll see the graph will be like this. So this will be half chair, this is chair, this is again chair, and this much energy is for the half chair. Well, this is the base. Okay, so this one is for the this one and this one for the twisted boat, twisted boat. Okay, so and this one is for the boat, and this again for the half chair. So you can see, and we have learned one thing: more energy, it means less stability. I told you in the starting that energy is inversely proportional to the stability. So you can see half chair, twisted boat, boat. Okay, so these are having more energy, and the chair is having the less energy. That's why chair is the most stable form. So if I'll write the order of the stability, chair is most stable. Okay, by seeing the graph. Now see, you remember that energy is inversely proportional to stability. Okay, so first is the chair is the most stable. Then second will be which is having the less energy. Half chair, twisted boat, or boat? Yes,
Twisted chair, sir.
twisted boat. Then next,
Boat.
boat. Next,
Half
half
chair.
chair. Okay, so this is the order of a stability. Chair is the most stable, then we'll go for the twisted boat, then we'll go for the boat, then we'll go for the half chair. Okay. Last thing is the bonds. So if I'll make the chair form, just see the positions. Just because later on we'll do the RS rotation and more of the rotation types and conformation in this particular form. So this one is known as axial bond. This is called equatorial bond. Here A represent axial. Okay, E represent equatorial. So just remember the position how I'm making. Wherever the corner is there, that is A. So see corner here A, here corner A, here corner A, and here corner A, here corner A. Wherever it is pointing, that will be the A. This is E, then this is E, then this is E, or this is E, and this is E. Wherever the corner is pointing, that will be considered as A, and in the neighboring atom, this is E. So now you can see in this particular form, you'll see all angles are 109 degree 28 minutes. Okay, so now there's less, or you can say around no angular strain. So this particular form is stable, most stable form. If I talk about the relative energy, see chair form is having 0.000 kilojoule per mole. It means zero energy. So energy is zero, it means the maximum stability. If I talk about the twisted boat is having 22.2 kilojoule per mole. Boat form is having 28.9 kilojoule per mole. So you can see the energy is increasing. Half chair, which was a least stable form, or you can say 44 kilojoule per mole. So see, you can see the energy difference also. So energy is inversely proportional to the stability. That's why the chair form is most stable. So this was in the chair form. If I'll make in the board form, axial or equatorial, you have to tell. Axial is again wherever the bond is pointing. Where the bond is pointing. So this is axial, this is axial, this is axial. No, sorry. Wait. This is axial, this is axial, this is axial, this is axial, this is axial. Okay. And then equatorial, 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 or here equatorial. So you can make it like this. Okay. Just remember the board form, chair form, and then it will be done. Okay. So now we have finished this chapter of isomerism. We'll discuss the new chapter from the next class. Till then, you have to remember all the things, whatever I told you. Okay. So we'll see you in the next class and complete this. And we have completed 2 chapters of organic. First, we have done the some basic principles, and then we have done the isomerism. Now we have 2 chapters left, that is purification and characterization of organic compounds. Second one is the hydrocarbon. So I'll bring one PowerPoint presentation, most probably for your purification characterization. First, I'll explain every purification method, then we'll go for the hydrocarbons. Okay. So till then, just remember this thing and revise this thing. Okay. So see you in next class. You can join the next session.
Thank you, sir.
Most welcome, sir.
Students, please join the next session.